Happy learning! Today we're going to talk about shortest networks. Okay, so in a previous video, we talked about minimum spanning trees. And a minimum spanning tree was the cheapest way to connect all of the vertices in our graph using the edges that the graph has. Okay, today we're going to talk about the shortest network, which is saying, oh, maybe we could include additional vertices to the graph, and then we could actually find smaller or shorter spanning trees of this new graph that has more vertices. Okay, so what we're going to do today is we will add vertices in strategic locations to reduce the total weight of a network. Okay, let me give you an example. So suppose we have an equilateral triangle. Okay, and in today's, I'm going to try my best to draw everything to scale. And we're going to work under the assumption that our graphs are actually geometrically accurate. Okay, so suppose we have an equilateral triangle of side length 10. The minimum spanning tree of this graph is basically you pick two of the edges. Right? The minimum spanning tree has length 20. But what we're going to be able to do is if we include a point in the center, this point is going to be called a Fermat point. Okay, I know it's Fermat, but I'm American, so we say Fermat. And we're going to actually get a shorter network that looks like this. Okay, this network has a length slightly less than 20. Okay, and we could use geometry to get the exact length, but typically we would just use technology to do that for us. Okay, so the Fermat point is like this, is the point in the triangle that is closest to the 3 points. It basically minimizes the total distance from the 3 vertices. Okay, and so let's state a theorem. So given 3 points, and a triangle T, formed by these points, the shortest network connecting these points will either be Okay, one option is the shorter two sides of the triangle. Okay, when is it the case that it's the shortest two sides of the triangle? That's if one of the angles in the triangle is larger than 120 degrees. Okay, so if our original triangle looks something like this, this angle here is much larger than 120, at least I'm hope to draw one that was bigger than 120. And so the shortest network would be the minimum spanning tree. It would be, just these two edges. But if all of our angles are less than 120 degrees, then we find this Fermat point, and this would be our shortest network. Okay, so otherwise, the shortest network would be the three line segments connecting the Fermat point for T to the original three vertices. Okay, so let me now show you how to find a Fermat point. Okay, what we're going to walk through now is called Torricelli's construction. Okay, and I'm just going to, instead of writing out the steps, I think it's best to just show you how to do it. So this is Torricelli. Okay, and so this is going to be our way of finding Fermat points, and then we're going to use these Fermat points to get shortest networks. Okay, so to use Torricelli's construction, we need a triangle where each angle is less than 120 degrees. So suppose this is our triangle. Okay, so let's say it's A, B, and C. And so on each of the sides, we are going to make an equilateral triangle. Okay, so I'm going to try my best to eyeball this, but of course we could do this with a computer. All right, so these are each equilateral triangles. And now we're going to take opposite points and connect them with lines. Where these lines intersect, that's our Fermat point. Okay, so we have our original triangle. We glue equilateral triangles to each of the sides and then connect opposite points. And so our shortest network is the following. And that's our Fermat point. Okay, and this saves us a little bit of length. Okay, and what we're going to do is we're going to have a large graph, and we're going to find a bunch of Fermat points, and that's going to help us save on some length. Okay, so we'll now define what a Steiner point is, and the Steiner tree. A Steiner point is basically a Fermat point, but when we have a graph with more than 3 vertices. For a graph G, a Steiner point is a new point in the graph Okay, so we're adding new vertices to the graph. And this new point is going to have vertex degree 3. Okay, so it's going to look like this, right? Basically, you could picture Fermat points as Steiner points. Okay, it has vertex degree 3, and each of these angles is going to be 120 degrees. So in the 3 edges incident to P, each have 120 degrees. We're going to be interested in not just Steiner points, but Steiner trees. So a Steiner tree is a tree that consists of the original vertices and Steiner points. Okay, and so now I'm going to walk you through the Steiner network method. And this is a method for finding the minimum network, the smallest network. Okay, and so let me show you how to do that. Again, I could write out all the steps, but I think it's just best to show you. with an example. All right, so suppose we have the following graph. Okay, and suppose that this is drawn to scale. So these each have length, let's say 10, and then these have like length 14. That would be the length of the diagonal of a square. Okay, our first step is we need to find a minimum spanning tree. Okay, and so the minimum spanning tree would be 3 of the sides here. So we find our minimum spanning tree. And we are going to build a Steiner network from this. Okay? And so what do? We're going to be looking for triangles inside of our graph where all of the angles are less than 120 degrees. Okay? So we would take 3 vertices that are basically form a path. And we're going to put kind of a phantom edge here. And with this triangle, we're going to find the Fermat point. Okay, right, because each of these angles we would check either with we could measure the angles or we could have a computer check. Each of these angles is less than 120 degrees, so we find the Fermat point, right? So we'd build an equilateral triangle here, equilateral triangle here, equilateral triangle here, connect the dots just like we did two minutes ago, and we find our Fermat point, which is right around here. All right, now we're going to update our network. So we're not going to have this edge. We're not going to have this edge. We're not going to have this edge. Instead, we're going to have these edges. And if my drawing was correct, or if it was drawn accurately, this angle, and this angle would all be equal, and they would all equal 120 degrees. Okay, so if we're to try doing the phantom edge again here, remember the theorem says that our smallest network would actually just be these two edges. So there's no like Fermat point we have to add. And same thing if we added this phantom edge and this phantom edge. Okay, but we do have to check these three vertices. Because when we put our phantom edge here, this angle is less than 120, this angle is less than 120, this angle is less than 120. We need to find the Fermat point here. And so again, we would glue on some equilateral triangles, connect the dots, and we'd get our Fermat point would maybe be around here. All right, and so we now get rid of these edges and put in our new edges. All right, and then again, we would check. This is 120, this is 120, this is 120. This is, right, I just said 120. There's no triangle that we could make with a dummy edge, a phantom edge, that has all angles less than 120 degrees. So we're done. This is our Steiner network. Okay, and if we had some technology to actually measure these side lengths, this network is shorter than the minimum spanning tree. So if you use this Steiner method, you get a network that is better than the minimum spanning tree. So if you're trying to connect laptops to some central server and you want to save money on the cost of cable, you would use the Steiner method to figure out where exactly do I build these kind of junction points in the network. Okay, well, I hope you enjoyed this video and found it helpful. Yeah, this is really cool that we're using like geometry techniques now. Usually our graphs, it doesn't really matter where the vertices are, but today it's like, okay, we're representing things where the vertices are actually in this location, which I thought was pretty cool. Okay, well, let me know if you have any thoughts, and I will see you in the next one. Take care. Bye-bye.